saying, well, this actually could be what NASA thinks it is. And that's why this is so exciting. And that's why we want to have this press conference to share it with the world, to share it with you. And also, we are ultra transparent, right? If we had this exciting news about the peer reviewers and what we think we found at NASA, and I didn't bring it to you, if we didn't have everyone here together, you might go, you're trying to hide stuff from us. Why didn't you tell us that a year ago? So we are here to say this is exciting, and we want to share that news with, again, the data is...
On November 18th, a new amateur image of 3I Atlas appeared online, and at first glance, it looks like any other early capture of an interstellar visitor, a bright core surrounded by noise. But as more people examined it, one detail refused to blend into the background. 5 distinct points of light sit around the main object, spaced too cleanly and too consistently to dismiss without a second look. Under normal circumstances, this could be written off immediately as a camera artifact, diffraction, sensor reflections, or stray background stars. And in most cases, that explanation would be enough. But this week, Avi Loeb emphasized in an interview that if 3I Atlas were not a natural object, one hallmark could be the release of smaller units as it approaches Earth. He called them mini-probes, not as a prediction, but as a theoretical signature worth monitoring. The timing is what's raising eyebrows now. Days after that comment, an image surfaces showing 5 compact lights around the object, and the pattern does not neatly align with any single known optical effect. And this comes just as NASA prepares to release its first official spacecraft and telescope images on November 19. This is the data the public has been waiting for. Delayed, requested repeatedly, and increasingly important as the object continues to show behavior scientists are still trying to interpret. The question now is simple. After weeks of silence and speculation, will NASA's long-awaited images resolve the mystery, or reveal even more questions about what exactly is traveling through our solar system? The new capture from the amateur astronomer is now being examined frame by frame. Beyond the 5 luminous points, the image shows a sharply defined central core with a steep brightness fall-off, which implies a very compact, highly reflective nucleus. The 5 surrounding lights appear at consistent radial distances, arranged almost evenly around the object. That symmetry is unusual for simple diffraction or sensor artifacts, which typically produce linear patterns, repeating reflections or mirrored structures tied to the telescope's internal geometry. Here, the pattern does not align with the sensor grid, the telescope's known diffraction pattern, or any expected ghosting. The result is an image that is neither easily dismissed nor immediately alarming, but unquestionably worth deeper analysis. Some astronomers argue these lights could be background stars blurred by the exposure, but the brightness and falloff do not match typical background star profiles, especially when the comet's core is saturated. Others propose structured internal reflections inside the imaging sensor, yet those reflections should repeat at predictable offsets and intensities, which these do not. The arrangement is too clean to fit the usual offenders, but too ambiguous to classify as anything definitive. What remains is a pattern that occupies a strange middle ground, visually clear, geometrically consistent, but physically unexplained without instrument-specific modeling. And because this appearance follows Loeb's comments about smaller units around a main object, the community is giving this frame more scrutiny than it normally would.
This would already be notable on its own, but the broader context around 3I Atlas has become increasingly complex. Over the past months, Avi Loeb has been documenting a growing list of anomalies, 10 initially, now 12, that collectively push the object outside the behavior expected of a typical comet or asteroid. These anomalies include the unusually precise alignment of the object's trajectory with the plane of the planets, a probability Loeb places at less than 0.2%, its unexpected encounter distances with Mars, Jupiter, and other inner planets, an extreme brightness spike near perihelion, its unexpectedly blue color, which would require temperatures hotter than physically possible at that distance, and the emergence of a non-gravitational acceleration, meaning its trajectory has begun to deviate from what gravity alone can explain. One of the most significant anomalies emerged when 7 independent telescopes measured the rotation period of 3I Atlas, locking it in at 16.16 hours, This number is robust, measured repeatedly from July through August with negligible variation. Then came the discovery of massive jets extending millions of kilometers into space, captured earlier in November. Loeb calculated that at their measured velocity, it would take roughly 1 month for the gas to travel from the surface of the object to the visible end of these jets. But in that same month, the object would complete roughly 45 full rotations. A rotating body expelling material over that many full spins should produce a broadened, spiraling distribution of gas. Yet the jets appear narrow, coherent, and directionally stable, a configuration that does not align with basic angular momentum physics unless the jets are somehow collimated or driven by a mechanism more directional than typical cometary outgassing. Then there is the composition anomaly, nickel shedding with extremely low iron content, a composition that matches industrial nickel alloys, not known natural mineral distributions. Loeb has been careful with this finding, emphasizing that it is not by itself proof of artificial origin, but he also notes that this ratio has no precedent in known solar system comets. When combined with the object's mass, estimated at least 1,000 times greater than Oumuamua, and its trajectory through an unusually crowded stellar region near the galactic center where detecting it was more difficult, each new data point complicates its classification rather than clarifying it. The interview segment where Loeb discussed many probes was not a prediction, it was a reaction to these accumulating anomalies. His position has been consistent. If an interstellar object were technological, one signature could be the deployment of smaller units for reconnaissance or measurement. If such probes existed, they would appear as smaller, discrete objects moving with or around the primary body. Importantly, Loeb did not claim this is happening, only that if it were, astronomers should be prepared to detect it. It was an attempt to outline criteria, not to make a declaration. Yet days later, an amateur photograph appears showing 5 compact lights around the object. The resemblance is not enough to draw conclusions, but enough to intensify scrutiny.
Meanwhile, Loeb has been vocal about NASA's handling of existing data. The Mars Reconnaissance Orbiter captured the highest resolution images of 3I Atlas on October 2, about 30 kilometers per pixel, far superior to Hubble's earlier dataset. But the government shutdown began the next day, and no images have been released since. Loeb argues that scientific data should not be delayed by administrative or political events. He notes that the principal investigator of HiRISE is not a NASA employee, meaning the shutdown should not have impacted data distribution. Requests from members of Congress have also gone unanswered, and Loeb has expressed concern that the delay is preventing scientists from planning future observations while the object is rapidly evolving. NASA's upcoming November 19th release, therefore, carries unusual weight. This is the first time the agency will present spacecraft and telescope imagery since the shutdown and since the wave of independent anomalies emerged. Expectations are divided. Some expect low-resolution dots and haze, especially from the Mars orbiters, which are not designed for long-exposure comet imaging. Their push-broom sensors capture the Martian surface in narrow strips and cannot hold stable exposures long enough to reveal structure in a fast-moving interstellar object. At best, MRO will produce a small pixelated nucleus with faint halo, incapable of confirming or denying anything visible in amateur images. The best data, if included, would come from ground-based assets like the Subaru telescope, or from space-based instruments like Hubble or JWST should they have been allocated time. Those telescopes could reveal coma structure, jet geometry, and possibly the beginnings of fragmentation or asymmetric outgassing. But even they would struggle to resolve objects only a few tens or hundreds of meters across, if such objects existed around the main body. NASA's release will likely show structure, but not answers, complexity, but not resolution. This puts the scientific community in a rare position. The 12 anomalies Loeb outlined are independent observations, gathered from different telescopes, instruments, and analytic teams. None individually confirm anything extraordinary, but collectively they shape a profile that fits no familiar category cleanly. The jet's coherence contradicts the rotation data. The The color contradicts basic thermodynamics. The trajectory contradicts expected random interstellar arrival angles. The nickel anomaly contradicts known natural distributions. The mass is far outside the scale of previous interstellar visitors. And now one amateur image shows a pattern that doesn't neatly fit any standard optical artifact. In this environment, NASA's delayed imagery feels more consequential than usual. The agency's release could provide clarity on jet morphology, coma dynamics, and nucleus brightness. It could confirm whether the object's recent brightening is consistent with thermal activity or whether the non-gravitational acceleration is increasing. Or it could reveal new features that deepen the list of unclassified behaviors scientists must explain.
The question is not whether the object is artificial. The question is whether all these observations can be reconciled within known comet physics. If they can, the case closes. If they cannot, then the scientific community must expand its models. Whether that means new types of interstellar icebergs, new forms of volatile outgassing, or, in the most remote possibility, engineered behavior. What comes next will depend heavily on what NASA shows, what data remain withheld, and what new independent images emerge in the coming weeks. Loeb has mentioned that the International Asteroid Warning Network will begin a coordinated observational campaign from November 27th to January 27th, using assets across Earth and in orbit. The goal is simple: gather as much data as possible during 3I Atlas's close approach and determine whether any motion, light pattern, or structural change deviates from natural behavior. In the next hours, NASA's images will finally break the silence. They may settle the debate. They may complicate it. Or they may do something rare in science, open a new chapter in understanding interstellar objects, one driven not by expectations, but by evidence that refuses to fit neatly within the models we've used for decades. And whatever those images show, they will mark a turning point, either toward the most detailed understanding yet of a natural interstellar object, or toward confirmation that 3I Atlas is unlike anything we have ever encountered before.